Alright, so here we go. Let's do some more of these. So number 4 says find the nth partial sum. So this is sort of review from previous sections. Looks like we're trying to add this creature right here. Standard technique for this is try to use the partial fraction decomposition of this, which we do, and luckily enough we get a telescoping sum. All the stuff in the middle cancels, all you get is the endpoints. You can combine that by using the common denominator, and you get that the kth partial sum is 4k over 2k plus 1. Meaning that if you had to add 100 terms, for example, the sum of the first 100 terms would be 4 times 100 divided by 2 times 100 plus 1. Clearly that limit is 2, and so the answer is pretty straightforward there. Alright, let's go on to maybe try a different one, right? That one was way too easy. What do you guys think about this one, number 6? So number 6 goes something like this. They give you the function f of x equals x to the third and tell you to make the bridge. Now this is funny because it's already a polynomial, so you're making a bridge even from one polynomial to another one. This one is just x to the third, and the other one is powers of x minus 3. It's centered around x minus 3. That's what's amazing. They're both polynomials, yet you're making a bridge from within. But no worries. Our standard idea here, the celebrated formula for the nth coefficient, still works excellently here. So we go on and we produce the first derivative, the second derivative, the third derivative, all the derivatives, the corresponding coefficients according to the formula, and we expand it. Again, this is what you did in Calc 1, the best linear approximation. We're going beyond that, the best degree 2, the best degree 3 approximation. Plug in your numbers and you're done. Pretty straightforward there. Let's try number 7. Number 7 says, so you've got a power series here, an infinitely long polynomial, and you try to match it up with which function it's equal to. So because I noticed the n here on the power, I can see that it's a geometrics. It's one of the super famous ones. So I'm going to use my geometric skills on that one. It's going to go like this. The geometric sum, if it had started at 0, it would just be that, but it starts at 1, so you can factor out one of these guys. Then it looks like that. For any kind of stuffed triangle where the triangle is less than 1 in absolute value, that turns into that. Again, if this is less than 1, that vanishes and it turns into that. This becomes 0, so this becomes that. And so we get an excellent formula for the summation of the geometric sum starting at 1. It looks more or less like this. Now all we have to do is apply it to our specific problem. In our problem, this triangle stuff, the powers of, were the quantity x minus 6 divided by 3. So I plug that in there, plug it on the right hand side, and I'm done. Clean it up. Boom. Piece of cake. Easy money. Let's try number 8. Oh, you should skip number 8 because it's talking about the error. I mistakenly placed this on the quiz. We'll talk about this one on another day. Let's do number 9 here better. Number 9 says find the power series. Again, you got to find the bridge. You got to think that's not a polynomial. Which polynomial is it equal to? Standard question. So you could use your excellent formula here, which we've done many times, or you could get a little fancy here, a little creative. I notice that this is something, this is the derivative of something famous. Of what? I don't know. I'd have to take the integral and walk backwards. So I take the integral, and I realize that this is the integral. So therefore, if I take the derivative of this, I get that, and so you get this excellent equation. The derivative of this piece is equal to that. Now the reason I write it that way is because this one is hard to find the series for, the expansion, but this one is super easy because that's just a geometric sum, just like the one we did a couple minutes ago. And so instead of doing this, I'd rather do the expansion for its integral, because it doesn't have that square. So I look at this integral and I expand it, and then I take the derivative to get back where I was. And so by doing that, you see I took the integral, I got this, so I put a derivative here. I expanded this using I took out the 1/6 because that's just a constant. I recognize this is the famous one. This looks like, the one I just said, it looks like 1 over 1 minus triangle, which of course is equal to 1 plus triangle square, etc., etc., etc. We did this like 2 seconds ago. So I expand that. Now I take the derivative of that, and I get that, then I distribute it. Pretty straightforward. That's just an alternative way of, sort of a creative way of going around having to do this DNA stuff for every single term and every single coefficient in the expansion. All right, let's move on here. That was number 9. How about we do number 10? Number 10 is pretty standard also. You got a function here, and you want the expansion around x equals 6. So you got the function and you got the bridge. You got to figure out which one does it match up with. Again, we can use our famous formula here, and we can use fancy stuff here also. Let me see what I did here. I did just the standard stuff here. So I look at all the derivatives, and I look at all, and then I evaluate all my coefficients using this excellent formula, and then I plug them in here. This is the best linear approximation according to Calc 1, best degree 2, best degree 3, plug them in there. Pretty straightforward, and you get the answer, of course, is D. Alright, that gives you the first 10 problems. Hopefully that helps you guys out. Post questions on the forum if you got some more. I was going to do all 40 of them, but I thought that's overkill. Let me know if you guys need more help, alright? See you guys. Peace.